Hey guys, I'm so excited to get to tackle today's lesson with you. So thanks already for joining. I hope you had some good experience with the sugar and salt simulation yesterday, which kind of gave you an intro as to how different compounds can dissolve. Some dissolve as entire molecules, while others dissolve as breaking apart into ions. And so now what we're going to do is kind of step back and take a broader look at what a solution is, as well as how to do some important calculations about solution concentration and dilution. And if you decide to go on and take Chemistry 2, we'll spend a good bit of time digging deeper into this topic toward the beginning of the semester, and that's a really fun unit that I enjoy getting to teach. So first of all, let's just get some basic definitions down for what a solution is. So a solution consists of two parts. The first part is the solute, which is what is being dissolved. The second part is the solvent, and that's the substance doing the dissolving. All right? So the solute is dissolved in the solvent. Doing the dissolving. Get that all written down for you. There we go. All right, so solution consists of solute plus the solvent. And typically the universal solvent that's very good at dissolving a lot of things is the substance water, H2O. And so you'll see that kind of as the basis for a lot of the solutions that we'll run into. And oftentimes the phrase that you'll hear in that case is it will be called an aqueous solution. And so that just means that the solvent is water in that case. All right. So what we're going to do first is kind of review what you learned yesterday in the simulation, that different solutes dissolve in different ways. So what happens when you have something that's an ionic compound, which is consisting of a metal and a nonmetal, those are going to break apart into ions when being dissolved. Then what happens is the solvent molecules will orient themselves to account for the charges of the cations and anions. So yesterday you looked at sodium chloride. When that breaks apart, you generate sodium +1 ions and chlorine -1 ions. And the cations are typically smaller than your anions. And so what happened when we had the water molecules, they oriented themselves to be favorable in terms of attractions. And so if we think about our water molecule, you may remember from earlier studies that it's polar. Oxygen, since it's more electronegative, takes on a partial negative charge. Hydrogen, being less electronegative, takes on a partial positive charge. And so what happens, since sodium is a positive ion, the water molecules will surround it in a way that puts oxygen, which is partially negative, closest to that positive sodium. And so again, opposites attract, so a partial negative next to that partial positive is a good thing. The opposite is true for chlorine. So when the water molecules are in the process of surrounding chlorine, they'll approach it from the hydrogen side. Now what this does, since chlorine is negative, it puts the partial positive of our hydrogens closest to that negative charge. Again, opposites attract, so that's what makes this arrangement more favorable. All right, and they kind of form a cage around the ions, which is what is able to pull them into the solution and help them dissolve. Now, on the other hand, what we learned about covalent compounds, which consist of nonmetals, is that they remain as whole molecules when they're being dissolved. So, for example, your sugar molecule. When it was placed into water, it stayed as an entire sugar molecule, C12H22O11. So you had your entire molecule, and the waters would just kind of, surround it and interact with it as is. And so that's the difference between ionic and covalent compounds. Now, it's sometimes helpful to know how much stuff you've actually been able to dissolve in your solution. And that's where this idea of concentration comes in, okay? And so concentration is measured in terms of something called molarity. And the way that's defined is it takes the moles of solute per liters of solution, okay? And so when we place that kind of together in a formula, we have a big M, which stands for molarity. So in other words, this is just the concentration. And the formula is going to be moles of solute per liters of solution. Or sometimes you'll see the formula condensed to just moles over liters. All right. And so if you've ever made kind of Kool-Aid before, this concentration factor can come into play. You have your solute, the Kool-Aid powder, and the sugar, and then your solvent is water. And so let's pretend that you add, too much water. What that does to the concentration is lowers it, and your Kool-Aid kind of tastes weak. You're not very good. But however, let's pretend that you add too little water. What that does to your concentration is raises it, and so your Kool-Aid may taste strong. Or maybe you add too much sugar. That can also increase your concentration and affect, how your Kool-Aid tastes. And so by manipulating one of those factors, either the moles of solute or the liters of solution, you can affect the concentration overall. All right, so let's go ahead and look at this drawing. So first of all, we've got kind of a particle drawing to represent concentration, and we're asked which substance would be more concentrated. Now it's important to note that each of them are at the same volume. So probably, if you've taken a look, you're probably going to guess B, because it has the most moles of solute particles per the same volume or liters of solution. And so now what we're going to do is take those concepts and actually use them to make some calculations. So we'll work through a few examples together before we let you practice on your own. So the first one says 0.5 moles of sodium chloride is dissolved to make 0.05 liters of solution. What is the molarity? So I've got our variables listed out to the side, and let's go through and write down what we have. We know that we have 0.5 moles of our solute sodium chloride, and that it's been dissolved to make a total of 0.05 liters of our solution. They're then asking us to solve for the molarity. So we'll start by writing our formula. Big M equals moles over liters, and we'll plug in what we know. We know that we have 0.5 moles of our solute, and we'll be dividing by 0.05 liters of our solution. When you plug that into your calculator, we get 10 molar. And for the sig figs, it's kind of the same rules. So you go based off of the least number of sig figs. This 0.5 just has one sig fig, so we'll want to leave one sig fig in our answer. So this is a pretty strong molarity. And so typically, just in case you're curious, when we get chemical shipments, like for our lab, let's say we're getting in some hydrochloric acid, it comes in a big, ginormous kind of bottle, and it's normally in a concentration of 12 molar. I mean, that stuff is, it's really, really potent. And so typically when you guys work with the hydrochloric acid in the lab, most of the time it's either 1 molar or something like that. So it's a lot, less strong than those higher concentrations. All right, so now let's take it one step further and work a second practice problem. So in the lab, when you're creating a solution, you don't have a device that measures moles directly. Instead, you're more often working with grams, all right? But the thing is, now that we've been in chemistry for a while, we know how to convert between grams and moles using the molar mass of whatever the substance happens to be. So when you're doing a solutions problem and you see grams, just know that you're going to have to convert to moles. So we'll go to our periodic table and look up sodium's molar mass, which is 22.99. To that, we'll add chlorine's mass, which is 35.45. That tells us that we have 58.44 grams per 1 mole. So we'll start from the left and we'll do 1 divided by 58.44 times 1. That gets us a total of 0.017 moles with 2 sig figs. So now let's fill in our liters. We've been given 1.34 liters of solution. And again, we've been asked to solve for the concentration, which is just the molarity. So let's write our formula. Molarity equals moles over liters. We know that we have 0.017 moles of our solute, and then we'll be dividing by our total liters of solution, 1.34. Well, you'll plug that into your calculator, and what we get for this problem happens to be 0.013 molar. So again, 2 sig figs based on the 2 sig figs in the moles. And this is a lot less concentrated than the 10 molar solution that we just solved for. All right, so now let's go to this next problem right quick. And you can see these problems are a little bit faster than some others that we've worked in the past. So in this case, they actually tell us the molarity of a solution. They tell us it's 0.5 molar, and they let us know that we've used 1.34 moles of our solute. So this time, what they're asking us to solve for is the liters of solution. All of our values are in the right units, so we're ready to proceed. So we have 0.5 molar for our concentration, and we'll set that equal to the number of moles, 1.34 moles, divided by the liters, which is what we're looking to find. All right, so we're going to treat liters as if it's our variable x that we're solving for. And a quick little trick, you can either work this out kind of the long way, but if you have your variable in the denominator and it's set equal to one single value on the left, these two values can swap places very easily, and that rearranges your equation to where you have your moles divided by your molarity. There we go. Or if you'd rather, you can cross multiply as well. I know some people like to do that. So we'll go ahead and divide 1.34 divided by 0.5, and that gets us to 1 sig fig. Or well, first of all, let me show you what it is before we round. So before rounding, it's 2.68 molar, but our starting molarity value only has 1 sig fig, that 0.5. And so when we round off, the 2.68, if we're rounding to 1 sig fig, is going to round to just 3 molar. Okay, let's see. I think this is, I've got a choice here. Let me pick one more for us to do so we can save a little time. Okay, here we go. Let's skip down to maybe number 3. So this one says, what is the molarity or concentration of a solution made of 4.3 grams of sodium chloride dissolved in 2.3 milliliters of water? All right. So we're getting a little more practical, where again, they've given us grams, and so we're going to have to solve for the molar mass to be able to convert. So we've got 4.3 grams of sodium chloride, and then we'll convert to moles by using the molar mass, so which tells us the grams of sodium chloride per mole. We just calculated that earlier, which is 58.44. So we'll go ahead and divide 4.3 divided by 58.44, and that gets us to 2 sig figs, 0.074 moles of sodium chloride. Now we have something else that we haven't quite encountered before. Here we're told that it's been dissolved in 2.3 milliliters of water. This is also more practical for the lab because typically you're working with a graduated cylinder or perchance a volumetric flask, which measures in terms of milliliters. So what we'll have to remember is that a liter is 1,000 times bigger than a milliliter. So if we want to go from milliliters to liters, we need to divide by 1,000. This is the same as moving your decimal place 3 times to the right and filling in zeros for placeholders. So converting 2.3 milliliters gives us 0.0023 liters. Now we're ready to plug in and solve for the molarity. So our molarity formula is big M equals moles over liters. We'll plug in our moles, 0.074, and we'll divide by the number of liters, 0.0023. And so again, on these problems, it's just really important to keep up, with your units and make sure your units match the formula that you're using. All right, and so what I'm getting for this one, rounded to 2 sig figs, is 32 molar. So wow, that's a lot of salt and a little bit of water. So our solution is really concentrated. All right, so now what we're going to do is, now that we've covered the basic concentration problems, is we're going to spend a little bit of time talking about how to actually dilute a solution. So when you're diluting a solution, you're lowering the concentration. So a dilute solution will have a lower, or a weaker, so to speak, concentration than the starting solution. And so what we do when we're diluting a solution is we have to increase the volume of the solvent. And so typically the way that manifests itself is that we're going to be adding more water. All right. And so I want to show you this little picture right quick that's kind of interesting. So kind of the before and after the dilution. So first of all, one thing you'll notice is that the color of the solution is lighter when it's less concentrated. So that's kind of one effect that we see. But what we also see is kind of the increased volume level. So your dilute solution should have a greater volume of the solvent, all right? Now, the interesting thing is, let's pretend we had some Kool-Aid, so to speak, and we mixed it up and we decided it was too strong, and so we added some more water. In that process, what we didn't change was the amount of Kool-Aid powder and the amount of sugar that we had originally added. So when you're doing your dilution, what you're changing to adjust the concentration is actually the volume. So the liters, this is being changed or increased, and the moles of solute is actually staying the same. So we're manipulating that bottom factor of volume while keeping the moles of the stuff we dissolved the exact same. And so what happens is, if the moles of what we start with is equal to the moles of what we end with after the dilution, that allows us to generate kind of this neat formula that's called M1V1 equals M2V2. And so for those that are interested, let me kind of break it down for you right quick. So if you remember, that big M stands for molarity. And what it means by 1 is your starting molarity before the dilution. The V stands for volume, which is measured in liters. So then if we repeat that kind of on the other side, you're just looking at the molarity and the volume after the dilution. So what's neat is the units of liters cancel out on either side, and they leave us with our starting moles being set equal to our ending moles of solute, which is exactly what happens in dilution. All right, so now let's put that formula to work and work out a few practice problems. We're almost there, so thanks for hanging with me. Okay, so if 25 mils of water is added to 125 mils of a 0.15 molar sodium hydroxide solution, what will be the molarity of the diluted solution? Okay, so let's start just like we did before by listing out our variables. So first of all, let's search for our starting molarity. They tell us that we're beginning with a 0.15 molar sodium hydroxide solution. All right, now we need to figure out the volume of that solution that we're starting with. So if we read carefully, it says if 25 mils of water is added to. So that means that we are starting with the 125 milliliters, and we're going to be adding some additional water to it. Now what that does is help us figure out the second volume. If we take 125 milliliters and to that add 25 milliliters, that gives us a total diluted volume of 150 milliliters. The nice thing about the dilution formula is, since the liters kind of technically cancel out within the formula, we can use milliliters just as long as all of the volumes are in milliliters. Then that gives us all the information we need to know to solve for the second molarity after dilution. So let's write our formula in. M1V1 equals M2V2. Let's plug in our first molarity, 0.15 molar. Our first volume, 125 milliliters. we're solving for our second molarity after dilution. And then our second volume, the volume after the dilution, is 150 milliliters. So to solve for M2, we'll divide both sides by the 150, and that should result in an answer for us. So we'll do 0.15 times 125, then divided by the 150. And that generates a molarity of 0.13 molar. And that's the 2 sig figs like the other starting molarity. And just like we predicted, the molarity should go down, when we're diluting something. All right, let's try another one right quick. So this one says how many liters of a 0.05 molar HCl solution can be made by diluting a starting solution of 250 mils of 10 molar HCl. So I just picked up there on a key word that said starting solution. So our M1 and V1 are going to be 10 molar for our starting molarity and 250 milliliters for our starting volume. Now, what they're asking us to find here is how many liters we can make when we dilute it. So we're going to be solving for the second volume. And so the final molarity that they want us to achieve is 0.05 molar. And that's a lot more dilute than the starting 10 molar that we began with. All right. So, sorry, I'm technical difficulties here. All right, so let's go ahead and see what we can do with our problem now. So we've got our formula, M1V1 equals M2V2. Our first molarity is 10 molar. First volume, 250 mils. Our second molarity is 0.05 molar. And then our second volume is what we're looking for. So again, to solve for that second volume, we'll divide by 0.05 on both sides. And those will cancel out. All right, so let's see what we get. So 10 times 250 divided by 0.05. Woo, that's crazy. So our V2 is going to be 5 with 4 zeros, 50000. Now, here's the question. What are our units for volume in this case? So the way we know that is the volume 2 is going to have the same units as volume 1. So right now we are currently in milliliters. And so if our problem asked us for liters, we need to go ahead and convert back to liters. So again, just as a reminder, when you're going from milliliters to liters, we're dividing by 1,000, which means we move the decimal place 3 spots to the left. So in reality, we're dealing with 50 liters here for our volume. All right, so that's a lot. That's like 25 2-liter sodas. Okay, and then I think you guys, if you want, you're welcome to try the last problem. The answer is here, but I think you should be good with the examples that we've worked so far. So I won't keep you on here any longer than I have to. All right, well, good luck as you practice. Thanks so much for spending some time with me learning about molarity.